So yeah, hi everyone. My name is Jonas. As he just said, I am originally from Switzerland, but for the past 5 or so years, I've been living in Tokyo, Japan. And before I get started, just very quickly, I work for a company called HDE. We're also a sponsor here at PyCon Colombia, and one of the coolest things I think that we do is a thing called the Global Internship Program, where we will take students or people who just graduated or even people who are mid-career, and you can come have an internship in Japan for 6 to 8 weeks in our company. We'll pay your flight tickets, both ways of course, giving you some money so you can have a place to stay and food and have fun. And if you're interested in that at all, we have a booth in the other building, and we would love to have some people from Colombia, from anywhere in the world, join us. And if you have feedback about my talk, if you want to complain about what I just said, what I'm saying, you can do so on Twitter. If you want to see some code that I wrote, my GitHub is github.com/OJII. And our company website is hdecodejp.com/en. So yeah, let's get started with my talk, why you might want to go async. So I came up with this title, and the more I worked on this talk, the more I realized that it's a really, really terrible title. So let's not do that, because before I can tell you why you might want to go async, I have to actually tell you what I mean when I say the word async. So let's look at the word async. Async is short for asynchronous. And specifically when I say async, what I mean is asynchronous I/O, asynchronous input and output. And even more specifically, asynchronous input-output as it relates to networking. So servers, HTTP clients, database servers, web servers, that kind of thing. And very simply, it's the opposite of synchronous. And maybe the easiest way to explain this all is to just give you some examples of what are synchronous networking libraries in Python and what are asynchronous networking libraries in Python. Maybe this makes everything a bit more clear. Maybe the most popular or famous synchronous library right now in the Python world is a library called requests to do HTTP requests. A lot of you will probably have heard of Django, a synchronous web framework, very popular. Flask, if you want something a little bit smaller. If you need to talk to a database, you might use something like PsychoPG2 if your database is Postgres. If you're on AWS, you probably use Boto 3 to talk to the various AWS services. And actually, most libraries on PyPI will be synchronous by default. So let's look at the other side. What are some asynchronous libraries in Python? Maybe the oldest or best known one is Twisted, and I think the talk before this one was about Twisted. Twisted is a fantastic framework if you want to do asynchronous networking, especially if you want to talk all kinds of different protocols, because Twisted basically supports every protocol that ever existed. There's Tornado, which is personally what we use in our company. It's a asynchronous web framework, sort of on the level maybe of Flask, not of Django. There's async I/O now in the library in Python 3 since I think 3.5, which is kind of same level as Twisted or Tornado, but it's in the standard library, so that's cool, I guess. There's Sanic, which is basically the Flask for the asynchronous world. So it looks a little bit like Flask. You write it a little bit like Flask, but it's incredibly fast. There's also Curio, because async I/O being in the standard library doesn't mean we have to stop coming up with new ideas. So this is an alternative async implementation. Again, if you want to talk to a database, you might have AIOPG, which is an incredibly fast Postgres client. If you are on AWS, as we are, you use AIO Boto Core, which is basically Boto 3 for asynchronous I/O. And since it's me that is giving the talk, I will just shamelessly plug 2 libraries that I wrote. They're on GitHub, they're on PyPI. There's Arsenic, which is a asynchronous web browser automation tool. You might be familiar with Selenium. It's similar to Selenium, but it's asynchronous. And there's AAPNS if you want to talk to Apple push notification services from an asynchronous world. One thing, all these things are different implementations, different apps, but they all have some things that are in common and that they share all each other. And one thing they all have is something called an event loop. And the event loop is basically the thing that runs your code. So if you do asynchronous networking, you will have in your application, you will have one event loop, and the event loop is in charge of everything. Specifically, what an event loop handles is a thing called coroutines. And that is basically the solution that we've come up with to get rid of something called callback hell. If any of you have done any amount of JavaScript until very, very recently, where they kind of solved this with promises and then with an async await, you might be familiar with every function taking a callback argument, and then you have to have a callback argument again for that callback, et cetera, et cetera. So we kind of got rid of this, and a coroutine is a function which allows cooperative multitasking. And so it's short for cooperative subroutine. And the cooperative bit here is really important because it's different from things like threading or multiprocessing, where it's something called preemptive multitasking, which means the system that runs the code will decide what runs when. But in a cooperative multitasking environment, your code, the code that you're writing says, now it's okay to do something else. So you have to opt in and you have to actually cooperate with the whole system to make it work. And in asynchronous I/O, at least in Python, I/O, input and output, writing to a server, reading from a server, same for clients, is non-blocking. But importantly, logic code, as in CPU-driven code, is still blocking. So your for loops, your if statements, your while loops, those still block. But whenever you try to read from a server or write to a server, that should be non-blocking. So yeah, now that hopefully you have a basic idea of what I mean when I say async, let's go back to my title, why you might want to go async. And I'm actually not gonna wait too long here, and I'm just gonna give you the answer, because the answer is simply money. So maybe a better title than why you might want to go async would be, why does going async save you money? Now, if any of you have done Python for any amount of time, you might have heard people from other languages or even people from within Python saying that Python is incredibly slow and that's a bad thing, and that's why Python will never be useful for anything, and you should not use it because it's slow. And one problem, especially if you're writing a website or a web server or a server in general, is that by default in a synchronous world, if you're doing Django, if you're doing Flask or anything like that, by default, your server can handle one single request per thread per process. So if you don't do anything special, your server will only ever handle one request at a time. And usually how we do scaling in that system is we either spawn up more threads or more processes. Usually you use something like GUnicorn to deal with that for you, but you have to run more than one process. You have to run more than one thread, and you very quickly need more servers. The problem with that is it wastes a lot of resources. An extra process costs a lot of memory. You have to have a whole other Python interpreter in there. Threads also have memory overhead, and there's a lot of CPU overhead because you have to schedule this whole switching around between tasks and processes. And one truism that a lot of people realize when building web applications especially is most of the time in your web application will actually not be doing anything useful. Most of the time it's just waiting for the database to respond to a query. And very little time is actually spent in your Python code. Most of the time is spent in your database driver waiting for the database to respond, or you wait for the client to send all the data, or for the data you want to send to the client to all be sent. So people say Python is slow, and I say that's, yeah, sure, that's true for some things, but maybe it's not that true for everything. I think Python is inefficient. And I also think Python is not inefficient, actually. It's actually synchronous Python that is really inefficient. So let's use asynchronous Python to come to the rescue and save us from all these problems. So yeah, I'm going to give you a very small example of a web server, first synchronous and then asynchronous, and how this looks and why maybe make it clearer how this works. And we're going to write a very simple web server. It handles a post request. It saves post data to a database. The database will return some sort of identifier, and we will return that as JSON. So let's write that in synchronous Python. And this is not a real web framework that we're going to use. We're just going to make one up. And so we have a handler function that maybe looks something like this. It takes a request as an input parameter. It returns a response. It first reads the post data from the request, then saves it to the database, creates a response object, and returns it. I hope that's somewhat understandable. Now, what happens if we have a request that comes in? And actually, we have two requests that come in. That's the little pink comments on the right. So we have first request and we have the second request. And they happen at roughly the same time. So the first request comes in. We read the data from the first request. Maybe the first request is on a mobile phone, so that it's not a good connection. It takes a while. Second request is still, we don't do anything with it. OK, we finally have the data from the first request. We start saving it to the database. Second request is still waiting there. Nothing's happening. It doesn't see anything happening. And maybe our database is fast. Maybe it's slow. It's taking a while. OK, it's saved. We can finally make our response and return it. And now, finally, the second request can start. Second request will do the same thing. Maybe the second request is on a really fast connection, and it goes really fast. But the second request had to wait all the way until the first request was done. So there must be a better way. And I say the better way is you do it asynchronously. So we rewrite it again in a fictional web framework using asynchronous. In the first line, we changed the def handler to async def. And we now don't return anything anymore, and we will see why in a second. An important thing to notice here is that although it says async def, the async keyword doesn't make your function asynchronous. The async keyword only marks your function as this could be asynchronous. And that's an important thing to notice, because on the second line, I inserted this await thing. And the await keyword is actually what makes your code asynchronous. We say await request get post data, which means while we get this post data, until we have all the data, something else can happen. It tells the system that runs this code that while we are waiting, do something else. And we do the same thing again with the database, because we're again waiting for the database connection to send all the data and get the response. And one pattern that you often do in an asynchronous world is you don't return a response object. Instead, you create a response object from a request. And then you write to it, and then eventually you say you've finished. And that way you can actually stream data to a client. Let's say you want to make a web handler that creates a CSV report that is a couple of megabytes large. In a synchronous world, you would build that all at once in memory and have that whole thing in memory and then send it all at once to the client. In an asynchronous world, you could send it line by line, or maybe a bunch of lines at a time. And you just write and write and write and write, and then eventually you're finished. So let's step through this again with our two requests that happen at the same time. The first request comes in. The first request hits the line where it waits for the post data. And while it waits for the post data, we can actually also handle the second request. It can also wait for post data. And again, maybe the first request is on mobile, and the second request is on a really fast landline. And so the second request actually overtakes the first request because it sends the data faster. Maybe the first request sends more data. And then they save it to the database, and they create a response object, and they're done. And so while we were waiting for I/O to happen, another request could be handled. Why does any of this actually work? So this is still one process. There's only one thread, one process. We don't do anything like that. But again, while we're waiting for data, we let other code run. So yeah, that was a whole bunch of code and kind of technical, so I don't know if everybody understood it. So let's try an analogy. Let's say you're opening a restaurant, okay? So you buy a nice little restaurant, a nice little location, in a good location, a lot of traffic, a lot of people. You open a restaurant, you hire some chefs in the back, you get some ingredients, you hire a waiter, you put a table there, and then your first customer comes. Yes, this is going to be great. So the waiter takes the first customer, gets them at the table, brings them a menu, and then the waiter waits until the customer is chosen. Now a second customer comes. And it goes like, waiter, I would like to eat. And the waiter just goes like, no. Wait. So the first customer chooses what they want to eat, and they say, waiter, please, yes, I would like to have this. Waiter brings the order to the kitchen. Kitchen starts working. The waiter, again, has nothing to do. Now there's like a whole line at the entrance of the restaurant. And the waiter just goes like, no, wait. No time. So the food comes, the food is done, the kitchen rings, and they bring out the food. Customer eats, eventually they pay, and they leave. And now we can have the second customer come in and be seated and have food. I've never owned a restaurant, I've worked in a restaurant, but I think that restaurant would not make a lot of money. There has to be a better way to run a restaurant, right? So in The synchronous solution to this would obviously be you buy the store next to the restaurant and the one next to that and next to that. So you have about 10 restaurants next to each other. And when a customer comes, you just send them to the nearest open restaurant. And you still have one customer per restaurant. And then you solve the problem. Maybe. You're probably going to go bankrupt very, very quickly. So there has to be a better way, right? So a better way would be you put a bunch of tables in your restaurant, and you maybe still only need one waiter. When a customer comes, you seat them, you give them the menu. And while that customer decides what they want to eat, you can seat another customer. It's a crazy idea, but I think it might work. So whenever the customers are deciding on what to do or waiting for their food to be done in the kitchen, during this idle time, the waiter can deal with other customers. And that's basically how asynchronous works. Whenever something has to wait for something to happen, we do something else. A little story time about what I did at work. So our main app that I work on, my team works on, is written in Tornado. When I joined the company, it was mostly written in synchronous Tornado. Tornado framework can do both synchronous and asynchronous. And so what I did is converted our most used APIs, our most used endpoints, from synchronous code to asynchronous code. Since this was legacy code, we mostly used threads at this point. So we throw all the I/O into threads. At this point, we are still on Python 2.7. And even doing this little thing already let us reduce the number of servers we need during peak time, which is Monday morning for us, by 25%. 25% less servers. For us, that meant saving a couple of $1,000 per month in server bills. So this was kind of a huge deal. And very importantly, our business logic, the thing we're actually interested in, stayed mostly the same. Because the business logic doesn't do I/O. We do the I/O and then give that data to the business logic, and that returns a result that we then send again to the client. And mostly what I did was, moving all I/O to either be real non-blocking using Tornado APIs or just into threads. And so I hope that by now you kind of get a feeling of why async might be a great idea. And so, again, maybe a better title for this talk of why you might want to go async, maybe a better title would have been why you might want to go async now. Because asynchronous networking has been around forever. Twisted, even in Python, we have Twisted, which has been around for longer than I can think, longer than I did Python. So why is async so hot now? And I think a big reason for this is Python 3.6. Python 3.6 introduced the async and await keywords. Before that, we used generators, so the yield statement, to basically do the same, but it never felt quite right. And with the async and await keywords, it actually becomes fun and productive and nice to work with async code. It also introduced a bunch of things like asynchronous iterators and generators and context managers, which, if you're familiar with normal iterators or generators or context managers, you probably know why those are really, really useful. And so we also have them in the async world now. Another thing that happened, and that is mostly due to, I believe, async I/O being introduced in the standard library, which was a somewhat controversial topic for some people because we already have Twisted and Tornado, etc. But I think the biggest thing that having async I/O in the standard library did for Python is that people actually noticed async and got interested in it and started to write really good and interesting code. A very important project is the UV loop project, which took the event loop, the underlying system of Node.js, and ported it to be usable in Python. So it's a drop-in replacement for what the standard library async I/O module gives, just a lot faster. There's AIO PG, which is probably the fastest Postgres client there is, because at least according to their own benchmarks, they're faster than Golang in Python. I don't know how they do that, but they do it. And we got Sanic, which is Flask for async, as I mentioned before. In the past, doing asynchronous web programming in Python was not a lot of fun. You could definitely do it. There's Twisted, there's Tornado, but both of them don't have the same feel as Flask, which is very simple and easy to get started with. Tornado and Twisted are much more involved, and expect you to know a lot more from the get-go. And also, we started to get all these libraries that are prefixed with AIO, which stands for asynchronous I/O, of course. And so now you actually have client libraries for anything you need. You have an asynchronous version of that. You can talk to Amazon, you can talk to Postgres, MySQL, Redis, anything you want. So seeing that we have this fantastic stuff in Python 3.6, I have to continue my story from before, because before I mentioned we're still on 2.7, we're still using threads. So what I did is I took a week, spent a week at work and just upgraded our whole app to Python 3.6 without telling anybody. Because it's a bit hard to sell an upgrade to 3.6, so I just did it and opened a pull request and said, guys, here's Python 3.6, please accept this. And in the process, I replaced the Tornado main loop with the async IO main loop. I didn't do this because there's anything wrong with the Tornado event loop. It's just easier to use other libraries if you're using the async IO main loop, which you can just drop into Tornado. Tornado supports this. I was able to remove about 20 dependencies because we're now in Python 3.6, so we don't need them anymore. Stuff like Unicode CSV and other things. This slide is the status from about half a year ago, so now it's more like 50 dependencies removed. Thank you, Python 3. During the upgrade, I only had problems with 2 libraries. One of them was OAuth client, which is a Google API client. The problem with that was that there's a version that works on 3.6, but we were using a slightly older version, and upgrading actually was really difficult. Had nothing to do with the Python upgrade, just with the upgrade of the library itself. And because we only used a very, very small subset of the library, we just decided to write it ourselves. And the same with APNS. APNS is the Apple Push Notification Service. If you want to send push notifications to Apple devices, iOS devices. And again, because that is so simple, we just wrote it ourselves. And yeah, we started to use some async IO libraries, but we were still going quite light on that. And these days, we are using a lot more. And so yeah, the result of that was our request handling, the average response time for our requests became 4 times faster. At the very beginning of this whole journey of going async, we were sitting at around 400 milliseconds per request on average, which is quite terrible. And now we're well below 100. And much more importantly than it's getting so much faster is actually that before, our average response times were like a really crazy jitter graph with like huge ups and downs. And now it's just nice and flat. And the same thing happened actually with the CPU again. It went, again, much, much lower and became much more stable. I can't really give you percentages or speed ups or anything like that because this whole thing, the process happened over a while, and we kept just removing servers and changing everything because we didn't need as many servers anymore. So it's a bit hard to actually track how much better it got. It just got a lot better. But what I know is that we reduced the number of servers by another 30%, or it's even more now. We keep just removing servers every week, basically. And so the whole thing, yeah, saved us a whole bunch of servers and money. And we didn't have to do all that much. So yeah, to recap, you should use async to save yourself money. You should use async now because it's ready. And you really, really, really should use Python 3.6 or very soon Python 3.7. Do yourself a favor and use Python 3. And yeah, with that I'm done. If you have any questions, I believe we have some time for that. And if you want to ask questions, you can do it now or later on Twitter or see me around in the hallway. And thank you very much.
How will you handle the migration if you can? It's not something that you cannot do yourself in a week, and you know that sometimes, like in a little bit larger teams, let's say 5 to 10 people, we don't really like pull requests that are like 3,000 lines plus 500,000 lines minus.
You mean the migration to Python 3?
No, I mean to async IO.
To async IO, the migration is going to be depending on what you're using right now. So if you're using Django, yeah. I'm sorry, but you probably have to rewrite your app. At that point, like your migration, the best thing you can do is just try to split your code into Django code and your business code, and have that be as separate as possible. And then you basically have to use a different framework to do your I/O, to do your HTTP. And so there's no easy way in that case. If you're using already a system that allows either async or non-async, so Twisted or Tornado, something like that, you can actually do it gradually. We do that. We still have synchronous code in our code base. It's just APIs that are used very, very rarely. So we don't really care about them. We care about the API that gets hit 90% of the time, and we make sure that that one is as efficient as possible.
And you mentioned Sonic a couple of times. Yeah. And yeah, I have used it for little projects. But does your company have a little bit of Sonic code already running on production? Yeah,
we have one small Sonic app that is basically a authentication proxy between Elasticsearch and Kibana and the outside world. So it's like a 100-line app. It's not anything big. Like Flask, Sonic is very micro, so I don't know how well it scales to massive projects. Very personally, I probably wouldn't use Sonic. I prefer AIO, HTTP, or something like that, yeah.
Thanks for the talk, it was awesome.
Thank you.
When you mentioned about doing the PR for the migration to async, how hard was to migrate the tests? That's one question. And the other one, just for try to remember, what was the thing that you said that is more fast than Golang?
Okay, I'll answer the second question first. The thing that is more faster than Golang is the Postgres client. It's called AIOPG. Okay. And it's apparently just incredibly fast. So compared to the standard Postgres client in Golang, according to their benchmarks, it's faster. They made the benchmarks, so you can trust it as much as you want or not. For testing, unfortunately, the standard library unit tests doesn't support async. You can write async tests using the normal unit tests module, but it's not going to be fun. It's going to be really painful. So what I did instead is change our test runner to PyTest. And PyTest can run unit tests, normal unit tests, so you don't have to rewrite your tests. But PyTest has really good support for async I/O. So you install a plugin called PyTest Async I/O, and then you mark your tests as being async, and then you can just write async functions to do your testing, and that's really useful. But yeah, rewriting the tests from synchronous to asynchronous was not the most fun. But actually, it's because we're using PyTest now. It's actually the whole thing actually had the extra benefit of we are now using PyTest, which means writing tests became a lot more fun and easier as a side effect. Yeah.
Thank you. Thank you for that.